Dear students, in this lecture we will prove the result that every convergent sequence of real numbers is bounded. Let us prove this result. Theorem: if Sn n is equal to 1 to infinity is bounded sequence of real numbers, if is bounded sequence of real numbers, then Sn n is equal to 1 to infinity is bounded. In words, we can describe this theorem as every convergent sequence of real numbers is bounded. Let us see the proof of this. Let L is equal to limit of Sn as n tends to infinity. Why this limit exists? Because it is convergent sequence. What is convergent sequence? Sequence is convergent if limit exists finitely. So let L is equal to limit of Sn. By the definition of limit of a sequence, by the definition of limit of a sequence, there is n belongs to I such that whenever n is greater equal to n, distance between Sn and L is less than 1. Distance between Sn and L is less than 1. So for every epsilon there is n such that this property gets satisfied, and in this case we are taking epsilon to be 1. So by one particular value we are considering natural number n satisfying this property. Which property? That whenever n is greater or equal to n, distance between Sn and L is less than epsilon. This implies that n is greater or equal to n implies mod Sn, which is equal to mod Sn minus L plus L, and if you apply the triangle inequality, it is going to be less than, better let me write here, it is going to be less equal to Sn minus L plus mod L, and which is less than 1 plus mod L. Thus what we have, thus we proved that n is greater or equal to n implies mod Sn is less than 1 plus mod L. Say this is statement number 1. So this statement holds for all n which are greater or equal to n. So we can take n to be capital N, n plus 1 and so on. Now there are finitely few terms which are left. Which terms are left? Up to 1 to up to n minus 1. So let us separately consider these terms. Okay. So we'll separately consider these terms. Take m dash as maximum of mod s1, mod s2, mod sn minus 1. Then whenever n is less equal to n minus 1, mod sn will be less equal to what? It will be less equal to m dash. Now say this is second statement. We want a number such that mod sn will be always less equal to m. So one can easily identify using these two statements. If we take maximum of 1 plus mod l or m dash, or any number which is greater than 1 plus mod l and m dash will work. So take m is equal to, say I choose a number which is greater than 1 plus mod l and m dash. So I simply add them and I take m to be this. Then it is clear that 1 plus mod l and m dash are less equal to m. Say this is third statement. From first, second and third, we can conclude that mod sn is less equal to m for all n, because n greater equal to n is covered here, n less equal to n minus 1 is covered here, and note that m dash with our choice of m, now we can write this. With our choice of m, we can observe this. So from first, second and third, we can write whenever n belongs to I, it is always true that mod sn is less equal to m. That is, mod sn is less equal to m for all n belongs to I. Hence the sequence Sn n is equal to 1 to infinity is bounded. Hence the sequence Sn n is equal to 1 to infinity bounded. So in verse we can describe this statement as every convergent sequence of real numbers is bounded. Every convergent sequence of real numbers is bounded. Of real numbers is bounded. The converse of this statement is not true. Every bounded sequence is not convergent, but every convergent sequence is bounded. Let us see an example for the fact that converse is not true. What is the converse statement of this statement? The converse statement is every bounded sequence is convergent, and it is false. So the converse is not true. The converse is not true for example, Sn n is equal to 1 to infinity, where Sn equals to minus 1 raised to n is bounded but not convergent. It is oscillatory sequence. It is divergent but not convergent. So remember, every convergent sequence is bounded but not conversely. Thank you.